to the course on FPGA-based signal processing systems. Today we'll be looking at the fast Fourier transform, which is a continuation of this sliding DFT and its variants. We have also seen the DFT equations. Using this fast Fourier transform, we can compute this k-bin indices or all the k-bin indices of this signal. So what are the coefficients of x of k for a given x of n? So this fast Fourier transform is an efficient computation, computationally efficient, so that to reduce the multiplications in the computation of DFT. Here we, as we have seen in the DFT, we have to correlate with the basis function sine and cos with the signal x of n. There is no need of such multiplications in the case of f of t. If we know the Twiddle factor and then stage by stage, that we could be that would reduce the number of multiplications in this comparing to the DFT. So the basically the order n square in the DFT computation, or n is the number of samples we consider for the DFT. Here order is reduced to n log n. So the log n is based on the radix here, which is used in the real-time processing. So the complexity especially reduces, and here we follow the divide and conquer algorithm, in which we take the x of n samples and then divide it by even and odd samples. That means separating them as even and odd, and then from even samples we again separate them even and odd, and then even and odd, so on. So if we do such things, so the n point DFT can be reduced. It depends on the stages and depends on the length. The number of stages will be reduced. So if it is n is equal to 8 samples, then we'll have 3 stages of computation. Up to say next first stage would be having dividing it and getting the 4-point DFTs, and then next will be this 2-point DFTs. So the first stage we will take the, if they take before take the stages of f of t. Before taking this f of t stages, we need to know what is the meaning of bit reversed. So here is that suppose the number of the samples are the x of 0, n is 0, 1, 2, 3, 4, 5, 6, 7. So here we have this 8 samples, for example, that indices of samples, the x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, 6, 7. So the 0 can be written in terms of 3-bit binary because we have only 7 in length. If we have 0 to 15, then there will be requirement of 4-bit binary. So in this case, the binary, the representation with 3-bit is 000. And the similarly 1 can be represented 001, 010, 011, 100, 101, 6 is 110, 7 is 111. So if you bit reverse this binary, which is 000, and 001 can be 100. So just reverse this bits. So take this first bit and put it in the last. This second one here, it is done this way. Okay, so the bit reversed. So here is this 0, which is at the last, and here and this one can be the order. So the if we take the 0, 1, 1, so the first bit goes to the last bit, and this and then this. So the order is reversed. So in that case, if you do this bit reversing in the binary indices of the samples, not the data, the samples, the indices, sample indices, that is going to be this 0 sample will exist as 0 only. This is showing the reversed one, and the 1 sample goes to the place of 4 and 2 goes to the place 2 retained there. This is 3 is becoming 6, and 4 is becoming 1, 5 is becoming 5 only, and then 6 is 3 and 7 is 7. So the bit reversed order would be this way. So if you say the index in proper order, in the order 0 to 7, whereas in the bit reversed order it would be 0, 4, 2, 6, 1, 5, 3, 7. So from this knowledge of this bit reversed case, how we are going to use this bit reversed in the FFT algorithm. Taking this, this FFT algorithms can be of 2 types computation, not only restricted to 2. So we take the the radix 2 here, that can be radix r, radix 3, radix 4, and so on. So the simplest one would be the radix 2, and we have these 2 types of decimation in time and decimation in frequency. So the DIT algorithms have this, we separate the samples in time domain, that is even and odd separation. Divide and conquer is performed in time domain. whereas in the samples division, whereas in the case of DIF we do that same thing in the frequency domain, frequency, the samples of frequency, that is x of k, and here is it's done with x of n. So we take the DFT equation which is x of k, this k is the bin index, and we have this x of n e power minus j 2 pi k n n n. So n is varying from 0 to n minus 1. So here if we take this x of n, so we are using this notation as well, so please note that changes of the square bracket or this unless until it is represented in the time domain. So this is the DFT equation in which so we have first taken this n samples and divide this whole x of n into, this is n is 2n and 2n plus 1. So first divide them into 2n plus 1. So that is this, when n is varying from 0 to n minus 1, that is, let's take for example n is 8, and that would vary from 0 to 7. Small n varies from the first equation 0 to 7. But here if we take this n equal to 0 to this particular endpoint DFT is divided in a sum of two computations. What are those things? N is varying from 0 to n by 2 minus 1, that is, you have the n 0 to n by 2 is 8 by 2, that is going to be 4 minus 1, that is 0 to 3, one set of sample, and then from here again we have this 2n. So if we have this is going to be 0 to 3 computation. Let us see that another 0 to 3 computation, what does it imply? So 0 to 3 computation as the summation, and 0 to 3 in this case as well. So the n which is having 0 to 7 now divided into two portions. This is made, n is made as 2n e power minus j 2 pi, in this equation make 2n and k n suffix n, and then n equal to 0 to n by 2 minus 1, that is another summation, because this way this would vary, n is varying from 0 to 3, okay, right? So 0 to 3, in that case this becomes 0. If n is 0, in that case this is x of 0 sample referring to x of 2. If n equal to 2, and that would be x of 4, right? If n equal to 3, then 3 into 2, that is x of 6. Okay, so 0, 2, 4, 6, these samples are considered among the 0 to 7 samples in the total. And then if you look at this portion, the n equal to 0 to again n by 2 minus 1, this indices n is varying here, but you can notice this x of 2n, this n is now replaced with 2n plus 1. So similarly this particular n is replaced with 2n plus 1. So in this cases, so what we get as a next set of samples, this is corresponding to this sample, and if we take here n equal to, in this case n equal to 0, that is referring to the x of 1 sample, and n equal to 1, 2 plus 1, that is x of 3, and the other one 2 is referring to 5, and then x of 7. So you can see that nicely these two equations, this particular summation taken of DFT is taking care of the even part of the samples, and this is taking the odd samples. Even and odd samples are separated this way. So we compute the DFT of even samples and then collecting the odd samples and its DFT. So this is summation of even the DFT plus the odd DFT here. So the simplification goes this way, that we have taken e power minus j 2 pi 2 into 2 pi 2 n k by n, which is going to be retained over here, and only e power minus j 2 pi into this k by n, okay, in excluding this this portion we have is e power minus j 2 pi k by n from the first equation. So retain this portion as well. As such, in this case only the e power minus j 2 pi k by n is taken as common, so that these two factors are retained in this summation. So what happens here, now we after taking this as common, Wn, we define this, the twiddle factor is e power minus j 2 pi n is 2 pi by n is w suffix n. So this is known to us, we are using it in the Wn. Also if we replace that e power minus j terms in terms of twiddle factor, this becomes Wn 2 power n and Wn 2 per nk, and the term which we have taken as common W suffix nk. So the summations varying from n varying from 0 to n by 2 minus 1 here. So x of k is there, and further simplification, if you see how we can simplify this term. So this is equal to Wn square, this or Wn power 2 is equal to e power minus j 2 pi by 2 pi by n power, this is 2. Okay, so here this can be written as e power minus j 2 pi n by 2. So in that case, this n can go as a, change this n as n by 2 here. That's the only change we do. So this is n equal to n by 2. This is retained as such here, this twiddle factor. There is no other change in the case of this particular next equation. So we have the two summations for n by 2 minus 1, 0 to n by 2 minus 1 samples. So this can give the DFT of the endpoint. So here k depends, of course this k can vary from 0 to n by 2 minus 1. So if we have this other portion, the k is varying from 0 to n by 2 minus 1, in the sense we have the k is 0 to 3, right? So k 0 to 3 can be obtained from this. What about the k 4 to 7? Okay, so in the DFT, when you want to compute the DFT for endpoint, you get x of 0, 1, 2, 3, 4, 5, 6 up to 7. So 0 to 7 k varying from 0 to 7. So you have to get the DFT of these bin 8 bin indices. So to get that, we just have this k plus n by 2, x of k is now added with n by 2, so that in the same equation the 2n and n by 2, now we have this k is now added with k plus n by 2. Similarly, every k is replaced with k plus n by 2. Here also the k is replaced with k plus n by 2. So in the previous equation, so now we can reduce this term, this particular term here, how we can take them. So if you multiply here w suffix n by 2 nk, this can be splitted like, and then w suffix n by 2 n into n by 2. Okay, so this summation, this can be simplified as e power minus j pi by n. So for all integer n's, this is going to be 1, and so this whole term can be simplified as w power nk by n by 2. So similarly, this term, that is w suffix n k plus o n by 2. This is the note the difference between this and this. You have the n over here, it doesn't have this n, then it is not, it depends on the indices of the time. So w suffix n k, so we can have split into two of them into w suffix n by 2, okay, the power. So this term goes as like minus 1, okay, minus j 2 pi here. So here we have 2 pi n by n, so 2 gets cancelled, minus j pi. So minus j pi is cos j pi minus j sin pi, so it becomes minus 1 to cos 180 here. So this term is becoming now as minus w suffix n k. So in the previous equation we had x of k, and the next set of equation is x of k plus n by 2. So now this equation reduces to w. So we have this term, and only the change over here is the addition of this two terms becomes minus in this case. So w suffix n k. Now from this, the set of equations what we have got in the first stage is one is x of k with the twiddle factor w suffix n power k, and the next one for x of k plus n by 2, the second equation, is having minus w suffix n k. So if you just compare these two equations, it doesn't, there is a only difference, this portion is added to it and this is subtracted from here. So the k is varying from here n by 2, 0 to n by 2 minus 1. From this we can call this particular DFT as, suppose, a fact g of k or some function. This is 2n point here, 2 into n, that is 0 to n by 2 minus 1. So half of the sample DFT, and there is a twiddle factor we have added, and this is another function which is for the, this is even and this is for the odd samples. So we get 1 x of k and then x of k plus n by 2. So this is this now we get for this k be 0 to 3. So we get from this equation we get x of 0 to x of 3. 1 to 3 for n equal to 8, whereas this second equation, this is also a g of k and is a twiddle factor w suffix n k here, and this is same as h of k. So from this we can say we get x of 4 to x of 7. This we can get from this equation. So we have splitted this obtaining DFT for the first half and the next half. So here 0 to 3 and 4 to 7. And now the first stage, now how do we get this? Here you can look at this. The samples are in bit reversed order. First we take 0, 2, k, that is 4, 6 and then 1, 3, 5, 7. So the even and odd samples splitted. But what we get is from here 0, G0, that is we have to take this 4-point DFT the first case to get x of 0. So g of 0, h of 0 and w8 0. Okay, so that's the first one. So what we got is x of k equal to g of k plus wn k here over here. Let's look at it here, wn k, okay, and h of k, right? So x of k plus n by 2 is giving g of k minus w suffix n k h of k. So using this equation, x of 0 is obtained, and then x of k is varying from 0 to n by 2 minus 1. From this we get this 4 of them, which is having this w8 0, w8 1 are referring to this, and here 4 is referring to these things. So we get from this 4-point DFT, and the samples you can take as 0, 2n, 4, x of 2n, okay. So is x of 2n and x of 2n plus 1. So these are odd samples and even samples. So when you feed that samples to the DIT algorithm, so this needs to be bit reversed order. This is the first stage of the computation. So once we have this, and we will also explore that what is that 4-point DFT again. Can we do it with 2-point DFTs? So the whole 8-point DFT first stage we have split into 2 halves, that is 4-point DFT, and similar way this is this 4-point DFT calculating 0 to 3, 0 to 3 for 2n. This is wn by 2 nk, wn by 2 nk. So the next stage comes taking this g of k, this is this term here. So this g of k's are this g of k, so which we have told us that is 2n, okay. So that 2n we can again we make it, so 4n and 4n plus 2, that is 2n, again divide that by n equal to, that is 2n plus 1. So we again make this 2n to 2n and 2n plus 1, again 2n plus 1. So gk is the one equation which is having, so when we divide this x of 2n is 4n now, and it becomes 4n plus 2, okay. So divided, so we can see the changes in the n, so and summation also that varies to 0 to n by 4 minus 1 here as well, this. So extend this to this, because k is varying from 0 to n by 4 minus 1, 8 by 4 is 2 minus 1, here 0 and 1 only. So 0 and 1 here. Similarly the other equation, if you want 4 of them, so we want here 0, 1, 2, 3, right, 0, 1, 2, 3 for in h cases. So we get one set 0, 1 from the first equation, and then here g2, g3 from the second set of equation, k plus n by 4, k again 0, 1, so this becomes 8 by 4 is 2, so it is going to be g of 2 and g of 3, okay. So we'll get it from here, and from this g0 and g1 we get from these two equations. So the same twiddle factor positive and negative among the, like what we got in x of k and x of k plus n by 2. So here k is varying from 0 to n by 4 minus 1. So it's the same thing we have to get it for the other half of this h of k also. So we name this as a function ak, bk, and ak and bk. So for the next stage, that is coming in the reverse direction. So take the h of k, that 2n plus 1 portion is again divided into 2n plus 1 and 2n plus 2 here. So this becomes 4n plus 1, and then here is 4n plus 3. So that we call as h of k. We refer this the summations again would be same. So similar to g of k, we have this h of k as well. So 4n plus 1, 4n plus 1. So this we call as again as a c and a d, which these are two different this taking the different samples over here. So dividing it again with the 2-point DFT. So now we have explored that g of 0, how to get g of 1, g2, g3 from g of k equation and the g of k plus n by 4 equation here. Similarly, h of k is obtained and h of k plus n by 4. Okay, so now we call this inputs of these functions as ak, bk, and ck and dk. There are 4 of them again. So now we reduce this to 2 points, 2-point DFT, and these functions are given af0, a1, b0, b1, c0, c1, and d0, d1. From that, k is varying from again 0, 1 only, that is. So now the order you can see x of 0, x of 4, x2, x6, this 2-point DFT takes here 2-point DFT. This one has another odd samples for 2-point DFT, odd sample 2-point DFT. So from this the butterfly comes. So this is one butterfly here, one butterfly structure which takes one actually complex multiplication and 2 complex additions. So these 2 portions of complex, because this is -1, it's simple, but if you have this w suffix n bar 0 or 1, 2, then it needs this computation multiplication here. That is having, if you take one, so this and this can be, this would be a one butterfly, okay, in this stage. Here this is 1. So we can take if we take this and this, and this is one butterfly, okay. So we have 2 here, 2 here, okay, that is 4. Similarly, in this stage we take this, suppose this is first stage, second stage, and third stage. Each stage has, so in this case 4, that is n by 2 butterflies are there. So each stage contains n by 2 butterflies. The 1, 2, 3, 4 you can see in this third stage, 1, 2, and then 3, 4, here 4 butterflies, 1, 2, 3, 4. Okay, each butterfly is computed this way, and you can reach out to from input to output by any means. The path can be any way. So if you want to compute x2, suppose you can choose this path, x of 0 and this x of 2, and or you can go from x of 2 to simply here by taking this value. So whatever the way you reach out the output, you will get from the input samples. So these coefficients are pre-computed for a fixed n. So these are going to be constant, and 3 stages are there, and only if you give the number of samples, then you can get the DFT outputs. So these are 0, 1, 2, 3. As we said, these are going to be complex conjugate of the first n by 2 minus 1 samples. So this is the 8-point DFT for containing 3 stages. And what are the computational complexity here? Suppose we take n as 8 here, because of the radix 2, we take 2 power m, write this number of samples you want to take the DFT as 2 power m. Number of butterflies per stage is n by 2, as I told here, this is n by 2, this is going to be n by 2. And number of stages, how we calculate is log base 2, that for radix 2 this is, the other radixes it would differ. So log base 2 per n. So n is 8 here, that is 2 power 3, it contains 3 stages. Okay, so that's how number of stages are computed, and computational complexity is decided by this complex multiplication and complex addition. So it has n by 2 log base 2 n, that each butterfly has one complex multiplication and two complex additions. So each stage, number of stages are log base to n, and in that you have at least 4 butterflies in each, that is n by 2 butterflies. Okay, so number of stages, this number of butterflies per stage, so is n by 2, and the number of stages are log base to n, multiply them. So we have only one complex multiplication for butterfly, and complex additions are 2, so the 2 gets cancelled, so we get this 2 gets cancelled, n log base to n is the complex additions. So this is the computational complexity, how it is getting reduced for log n in the order, instead of, in case of DFT we had this n square and n into n minus 1. So to compute this k f of t coefficients, so the if n is large, yes, it is giving very good. Maybe n is small, this and this, but doesn't make a difference. But in case of large values of n, yes, we have, this is giving the less computational complexity, in terms of complex multiplication and complex additions. In the DFT, we calculate all the k values, FFT also all the k values, but STFT we compute for one particular index, either k equal to 1 or k equal to 3, which frequency we are interested in. Similarly, MSTFT and HTFT and MHTFT we had, what are the variants we had looked into. So if I don't want all these bins, only one is needed, then we can go for this particular STFT things. And moreover, if you want that only coefficients, again it is better. But if you want only coefficient, f of t would be better. But if you want the instantaneous x of k1 and x of 2 or something, then it better to use the STFT. And then in the case of decimation frequency, in decimation in time, we had this bit reversed inputs, and you get the ordered k. Here there are FFT chips available to just feed the samples, and the chip that would give the coefficients. Okay, now we take the decimation in frequency FFT, so the same radix 2, so radix 3 also can be done in a similar way. So taking this DFT equation here, x of n, so x of n w suffix n n k, and n is varying from n by 2 n minus 1. So we can split this samples n up to 0 to suppose 8, we have 8 samples, so 0 to 7, 0 to 3 as one set, and 4 to 7 as another set. So n by 2 minus 1 refers to, suppose n is 8, in that case 0 to 3, and from 4 to 7 we take this summation. So if we split this one as first set and then x of n, so how can we generalize this equation? So the n equal to 0 to n by 2 minus 1, retain this as such, and in this case we have this n by 2, can we take this also as a shifting? So n plus, if you change this to n plus n by 2, and this n can be varied from 0 to n by 2 minus 1. So changing these n's, modifying them, n plus n by 2 and n plus n by 2, we get the simplified form, the equation here. So whatever n plus n by 2 is taken as outside the summation. So now these two are equal, like when we have these two real factors, and only the samples needs to be changed here. So first n by 2 minus 1 samples, and then this corresponds to the next n by 2 samples. So 0, if it is, this is going to be 4, 5, 6, 7. So now e power minus j 2 pi k n into n by 2, this term is now reduced to, see here, e power minus j 2 pi k. Okay, so it depends on k which we are using this term. So k, it is minus 1 k, minus 1 power k. So replace this equation x of k as x of n, this is minus 1, and this term, and the common term which is taken, w suffix n n k. So this is for the x of k we obtained. So this equation, the DFT equation, can be simplified to have x of k equal to x of n samples plus the rest of the samples as minus 1 per k, and you can perform the DFT for 0 to n by 2 minus 1. So this, if we are going to decimate in frequency, so k is now made as 2k instead of time 2n plus 1, that as the sample. So now we have keeping the samples and focusing that 0 to 3 samples computation and 4 to 7 are taken care in the DFT, but the bin indices k is now made it 2k. So 2k here and 2k here, this k is replaced with 2k, and so this simplification, this becomes 1. So the 2 can be brought down here, so as an n by 2. Okay, so this is going to be this the simplification of x of 2k. Now yes, this is varying from k equal to n by 2 minus 1. Now the next odd indices x of 2k plus 1. Now replace this k in that previous equation as 2k plus 1 here, minus 1 here, also 2k plus 1. So and then simplify this minus 1 part 2k into minus 1. So that would be given as w suffix n from there, and this is the simplification minus we get. So x of 2k can be obtained from the one butterfly, that is x of n, here x of n plus n by 2 we have. Okay, this is x of 2k and x of 2k plus 1. Okay, so 2k is obtained by adding this. Okay, so with the total factor, this is 2k is x of n plus 2 n plus n by 2 into this summation here, and whereas this is computed with w n n. Okay, so here this is going to be having minus 1. Okay, so this is the butterfly in this case. So after that subtracting this and then multiply by this factor w suffix capital N and power n. So that is how 2k and 2k plus 1 are. But this is counting again the one complex multiplication and two additions here. Okay, so 2k plus 1. So considering these ones as g1n when there is a positive in 2k and g2n negative. Okay, so the into wn this factor. So the equation now we get the ordered sample are given, not bit reversed. It is not in decimation in time. This is decimation in frequency. So we can observe that the changes of even and odd over here. The first set to get G20, G10. So for G10 is x of 0 plus x of 4. Okay, so here, and these are just addition of the samples, two of them. This is contributing one butterfly, right? This is one butterfly. Okay, here we have, and G1, G2, so next butterfly and so on. So G1, 0, 1, 2, 3 are first one, 2, 0, 2, 1, 2, 2 and 2, 3 are the next one. So here W80, 81, 82, 83 are the W suffix n power n, the values we got it in the butterfly. So after this 4-point DFT is coming to be even and odd. Now again this G1k, which is the G1 where we replaced with G1. Okay, and summation if we vary that n by 4 to n by 2 minus 1, we get the same steps can be followed for n is equal to 0 to n by 4 minus 1. So we get minus 1k. So G1, so 2k is having the instead of n by 2 in the first case of x of 2k. We have the same terms, and 2k plus 1 results in minus with this total factor 1. Similarly, we do it, this is the case of G2, the next set 2k, G2, 2k plus 1. So we taken in the decimation time as G and H, here G1 and G2 for a difference here, taken G1 and G2. So G1 2 of k, that is G1 of 2k, G1 of 2k plus 1, and then G2 2k, and then G2 2k plus 1. So the four equations gives the next DIF. Here G1 which is having the first two terms, G1 which is having next to two terms, G2, and similarly this. So this is one set again here, G2 and G2 2, 3. So we can get the, so now this portion is now changed to the butterflies of them. So which is going to be 2 of them contributing one butterfly, and so on. So the rest of them, you can see the butterfly which is having -1 and then multiplied with 880, 881, 880, 881. So the 2 points now is changing to, again, now we get this G1 and name them as V1 and V12, or the whatever the way you like, V21 and V22. So we get the set of again the next set, going for this V1 and V2, V21, V22. So these are now named as DFT of this, DFT of V11N, DFT of V12N, DFT of V21, and DFT of V22K. From this, the final one comes into picture as so the 2-point DFT is V10, 11. So you can have the reverse order, that is these butterflies in the reverse order in the decimation and time and frequency. So we have this ordered samples. We are not decimating. Here with the, you can see the outputs 0, 4 even, 2, 6, and then 1, 5, and then 3, 7. So we have the bit reversed order, the K in bit reversed order, not the N. Okay, so we get this so similar to the DIT. We have this butterflies 4 per stage, n/2 butterflies per stage, 3 stages here as well. This is the first stage. Now this is second stage and the third stage here. So we have n/2 butterflies in each stage. N is here 8, so 8 by 8 2. So the butterfly has again after the one computationally, the total factor is complex multiplication and 2 complex additions required for butterfly. So n/2 log base to n is the number of complex multiplication, and the additions have n log base to n complex additions. So as in the case of DIT also. So with these butterflies and butterfly stages, computation would be valid in this case. So each bottom here will have -1 and these two will -1, and here all of them. So we have every, this is 2k and 2k plus 1 in one stage, and then other stage it is can be again divided 4k and then 4k plus 1, 4k plus 1 and 4k plus 3, so on. So n is again n plus n/2, n and n plus n/4, and so on. So that could not be generalized here. So I have just given this here as a butterfly thing. So this is one butterfly. So every butterfly will have this structure. The -1 at the bottom and -1, -1, and here, so each butterfly will have this. So there are four in each stage, and so this is about the DIF algorithm. So DIT and DIF algorithms, FFT can be computed in both ways, and if we want to know the K in each stage, that is we can even compute that in the case, and this is in place. So where whatever the path you want to get it, suppose x of 6 can be obtained from any of the inputs like that. All the K values are needed, then we'll go for this FFT algorithm at all. So in the STFT variants we had seen, just would like to introduce this DSP builder, which can be used for the development of Verilog or VHDL codes, and then dump those codes in the FPGA. So we had seen this STFT and its variants and the STFT block diagrams using the Simulink MATLAB Simulink blocks. So the same way the MATLAB Simulink blocks can be converted, or we can draw the diagram of this STFT, the transfer function, in the MATLAB Simulink environment itself using Altera's DSP builder. So this is a third-party tool which is provided by Altera, and now it is Intel FPGAs. So those tools needs to be installed along with the MATLAB Simulink by verifying the version of the MATLAB, which version you use it. So the compatibility can be checked for what is required for this DSP builder blocks to be made. So once you have this in the Simulink, you will get that Altera block set as a separate toolbox. So Altera block sets will contain this adder, delays, and then some input blocks, input output pins, all of them, which are very much suitable to the programming of this FPGA, or get the code of these HDL ones. So these are, for example, input block, and this is output block. So the input output, and this is an adder. So you can see the delay. The comb filter is made in the x of n minus x of n minus n, and this is also a delay and adder, which is this portion is called the same way what we have made in the Simulink. This is the resonator, and this is comb filter, and this is non-recursive part, and this is recursive. If you just compare the Simulink diagram which we had done in the SDFT. So would like to introduce this blue blocks now instead of the black ones. Now it is getting changed to the blue blocks using this DSP builder. So the gains used over here and the outputs here, this is in phase component, and this is quadrature phase, this component. So take this over a file, or it can be just to view it. You can simulate and view it, and you can see the signal compiler over here, and then the board which we are going to use, FPGA board. Here we have shown the board which we have is Stratix 3 here, but now we have the more the Stratix 5 and so on. So signal tap analyzer, which is a block which is available in that. So when you dump this code as a Verilog or VHDL in the FPGA, when it runs in the chip, then you can tap the signal through the signal tap analyzer from the points where we want to see the output. Suppose I want to see the output at this point, you can connect the signal tap analyzer here and tap the point and get the samples viewed. What is at this point, what is the output? Okay, so that can be viewed through the MATLAB Simulink environment. So there is a clock over here. It's a global clock which depends on the board which you are using. Every FPGA board will have the clock, which is here it is 20 nanoseconds, actually 50 megahertz clock. So you have represent this as clock. So these decisions are based on this clock frequency, 20 nanosecond. And 20 nanosecond is very high for this. We use the suppose for to match the outputs what we got in the Simulink, just a 50 hertz is used. So 50 into 64, that is the FS we are using, 50 into 64, 50 hertz and 64 samples per cycle. That's too much, but we want to show this smoothness of the waveform. And here is that this mod counter. If you recall the digital part, when we have designed the counters, so you can see the real application, the ready-made blocks which are available for mod counter. We can fix the value what is this required. So 50 megahertz clock is divided to satisfy this FS, that is 50 into 64. So this count is used to reduce the divide by clock. So we get the samples over here, which are this clock samples are FS, this is 50 into 64. So that gets in that is enabling each delay used in the DSP builder. Okay, so that means this delay will be looking at this clock, not the global one. So, okay, this global is now divided and using this as a clock here. And there will be global reset. This is corresponding to the reset. You can see there is a this is clear, that is a reset in each block. We have this reset, and gain as we use in the Simulink environment. This is the gain here used here. This is 2 cos theta k, this part. Okay, and here we use the cos theta k and sin theta k over here, cos theta k and sin theta k here. This is implemented with the DSP builder for the SDFT transfer function, what we had learned already. The transfer function is now made it in the DSP builder blocks. So this is for the simulation, where the real-time simulation can be done, because the clock will be set at 20 nanoseconds, and you give the input accordingly and get the output for a suppose simple sine wave of 50 hertz, whether it is getting the in-phase and quadrature component or not. That's what is done over here. There is a input, this is x of n, and we can see this outputs in phase and quadrature components getting generated from the output. So this is still a simulation, but it's a real-time simulation. So the same thing, after making the code using this compiler, we can do the compilation process, analysis and synthesis and all those things, and get the code generated, then dumping into the FPGA. This is one way of targeting the FPGA. And similarly for MSTFT, we had also made this the DSP builder blocks, which has this you have the shifting the 0th bin, that index, and we show this complex conjugate parts, and then this is we have used the lookup table to generate the sine 2 pi kn plus j cos 2 pi k by kn. So that factor is here, and you have the comb filter part here. So you can also verify by constructing these blocks, and then we get the in-phase and quadrature components similarly using the MSTFT block. So the MSTFT again, this is to generate the cos theta kn and sin theta kn. Simply we put those n values of cos and sin in the lookup table and access this lookup table through a counter, the address, so that we can generate the cos and sin waves and then multiply them to get here. Also the HDFT block diagram can also be done with this comb filter. And we have this resonator block, we have that this is L, if you recall, L equal to 4 we have used, and then the thing here, this is the portion of which is having the which x of n sample and x of n minus n sample to be removed and x of n should be added. That is, this is implementing the update vector transform UVT. You can see the multiplications of the Tweedale factors we used in the 4 of in the L equal to 4 block. If you just compare this with the Simulink block which we had done, and this would tally, you can easily figure out that what are these. This is just a block to, as I told you, to get the samples reduced from 50 megahertz to this. So here we have not shown the board and compiler, so that can also be, that it can be added and the compilation can be done to generate the Verilog codes here. So with this HDFT also can be done in this way. So we have done with the Fourier transform like DFT and then STFT and its variants, DCT and then FFT. We had learned the theoretical part of it, and also how this can be generated in the blocks can be generated in Simulink environment and the DSP builder environment. This is for the Intel FPGAs or FPGA. Also this similar DSP, instead of DSP builder we can use the Xilinx FPGAs as well. In that case the third party tool is the Xilinx system generator. So a similar kind of environment is also available with as a third party tool for the Xilinx. So that is the another way of just the blocks, library blocks are available in a similar way that can also be used to develop these block diagrams. So and then code can be generated directly using Xilinx environment as well. This is through the DSP builder Intel FPGAs environment. So in the coming classes we will see how this block diagrams can be made as a code, Verilog or VHDL codes, and then how to download them in the FPGA to get these results and output. Here I have not connected the inputs. Similarly, the input and inputs are taken from MATLAB, and this scope is in the MATLAB output, but this will be in real time as an ADC and DAC outputs to be connected, ADC and DAC to be connected, and give the input through ADC, and this whole blue blocks will be in the FPGA, and through the daughter card ADC input signal will be fed and the output signal will be taken out through the daughter card of DAC, ADC and DACs. So we will show that in the real time demos, those things can be learned. Thank you.